Okay. Hello, everyone. Let's get started. So my name is Chris Hillier. I work in data center systems security at NVIDIA, focused specifically on systems like HGX, DGX, and MGX. Today, I'd like to spend some time sharing with you some work we've been doing at NVIDIA focused on device ownership transfer with the hope that we could bring this work to OCP and get your feedback. So first, I'd like to introduce ownership transfer. I'd like to introduce a problem statement that we believe is associated with ownership transfer. I'll then talk about our proposed solution. I'd then like to spend a couple minutes talking about how I believe the DOT is only the beginning, and we'll end with a call to action. So the existing OCP ownership transfer document defines ownership transfer as a process by which a device's recognized configuration owner changes from one entity to another and involves modifying state within the device. Generally speaking, for those of you who have been at OCP for a little bit, you know that ownership transfer goes by many names with many variations. At NVIDIA, we call it device ownership transfer, or DOT for short. There is sort of a religious debate about whether it's DOT or DOT. I'm firmly on the DOT side, just for reference. I've also heard transfer of ownership, ownership transfer, and dual signing is also a category of ownership transfer. So similarly, if you've been at OCP, you know that there's a wide range of opinions regarding both the scope and the mechanisms for device ownership transfer. So our problem statement. The industry generally requires a mechanism by which a device owner has strong assurances that only explicitly authorized firmware is allowed to be installed and executed on a device, which is a great statement, but in terms of device requirements, such as for a device vendor, what does that actually mean? It means that we have a derived requirement to enable device owners to be able to install a public key where said key is used for signature validation, ideally during both boot and firmware update of the device. Now with my sort of like grade school Microsoft Paint skills, you can see on the left we have a device that doesn't support device ownership transfer. We only have vendor keys in that device, and as such, any vendor-signed firmware can be installed and executed on the device. On the right, we have the device that does support ownership transfer. That device also has owner keys installed, and as such, only owner-authorized firmware can be installed. So in combination between sort of the definition of what is ownership transfer, along with the problem statement that we're facing as an industry, where do we go from here? So we propose that we abstract and expand upon an ownership transfer architecture that has already been built for NVIDIA Grace CPU. That architecture consists of 3 distinct device ownership transfer archetypes. We call them volatile, mutable locking, and DOT disabled, applied to 2 specific firmware types, which we call edit and no edit. We also propose limiting the scope of ownership transfer to only cover secure boot and secure update, but ensuring that the architecture we define is flexible for the future such that it can capture other things, say device configuration. We also propose an architecture that leans into attestation. As an industry, we've spent a lot of time and a lot of resources sort of building robust, trustworthy attestation mechanisms. We should use those mechanisms for ownership transfer. So you'll probably recognize the bottom half of this slide. I did ask Jeff for permission, but otherwise I stole it shamelessly from Jeff. This is a diagram that he previously put together where there's a spectrum of ownership transfer. On the far left, we have a device that has no ownership transfer, which in turn provides fewer security assurances to device owners, but also fewer circular economy roadblocks. On the far right, we have authenticated ownership transfer, which has been discussed at length in OCP, which does provide stronger security assurances given to owners, but does come with greater circular economy roadblocks. All I've done is I've taken Jeff's existing diagram, and I've superimposed the 3 DOT archetypes that we've come up with at NVIDIA. So you can see from the left, we have DOT disabled, which makes sense because it means you're turning DOT off. We then have volatile, followed by mutable locking. So in the next couple slides, I'm going to introduce or provide more detail about both the firmware types as well as the 3 DOT archetypes. After I do that, I have a state diagram that will hopefully help make the full architecture kind of click and coalesce for you. So I ask that you kind of like hang tough through the slides before we get to the state diagram, because it'll all start to make sense. The other thing I'll say before I get into the technical details is I am not what you would call a creative. So the naming scheme, specifically volatile, mutable locking, and edit and no edit, I've received critical feedback that they're perhaps not the most creative of names. So in addition to providing feedback for the ownership transfer architecture on the whole, I think we would also appreciate constructive criticism regarding how we've named and built this thing. because the names don't necessarily make sense, although the firmware types do. So what do those firmware types look like? So edit firmware, in an example of a very brute force naming, is a firmware type where the device owner has edit and authorship permission for said device firmware. As such, the owner keys and only the owner keys are used for signature validation. An example of this firmware type would be something like OEM UEFI. In contrast, our other firmware type, no edit, which again, creative naming scheme, is a firmware type where the owner does not have editor authorship permission for said device firmware. As such, we use both the vendor keys as well as the owner keys for signature validation, and a good example of this is any device where you have some sort of dual signing scheme or configuration. So now we'll step through the actual DOT archetypes. The first of those three archetypes, again, we call volatile. In volatile, the owner signing key is stored in volatile storage, which means it is erased upon a device power cycle. That owner signing key does not require either authentication or authorization for the initial installation. However, because the key is stored in volatile storage, there is a derived requirement for that owner signing key to be streamed to the device upon every power cycle. I think that makes sense. I'll step through it just a little bit more. So you can imagine that in order, if your ownership transfer is going to cover secure boot, obviously you have some firmware that's being stored somewhere like locally in SPI Flash, taking into account today's earlier discussions around streaming boot and such. That firmware image is going to have a signature that was generated using the owner signing key. You obviously need to provide the owner signing key to the device before you try to boot from that firmware such that it can successfully authenticate and the device can boot, right? Hence the requirement for being able to stream a key to the device. We also propose that the device returns to a default state upon a power cycle wherein only the vendor keys are used for signature validation if the owner signing key is never installed. So what are the pros of volatile ownership transfer? Well, the pros are really, and this has been discussed at OCP before, the pros are really focused on reduced lifecycle complexity. We only have one key pair. We only have one public key that needs to be installed on the device. It's the owner signing key, and device decommission is a breeze, right? You're basically just power cycling the device, and the key material is all erased from the device. You can then decommission it. You can scrap it, although I hope you don't do that with an NVIDIA GPU, and you can be on your way, right? But what are the cons associated with volatile? Well, the cons are really the key streaming piece, right? You have to make sure you get the right key in the right place at the right time, especially if you're going to use or use ownership transfers for secure boot, such that the device boots successfully. But then what about our second ownership transfer archetype? Mutable locking. So in mutable locking, we take that same owner signing key and we add a second key, which we call the owner locking key. The owner signing key is locked to the device via the installation of that second key, the owner locking key. Both of those keys are stored in non-volatile storage, and as such, they're persistent across a device power cycle. Now, similar to volatile, neither of those keys, so neither the owner signing key nor the owner locking key, require either authentication or authorization for initial installation. However, rotation of either of those keys, the owner signing key or the owner locking key, does require authorization via what we call an authorized unlock operation. More specifically, that would consist of something like a countersigning operation using the private portion of the owner locking key. You can imagine that the device would generate something like a unique one-time nonce. You then retrieve that nonce from the device. You sign it offline using the private portion of the owner locking key pair. You then reinstall the signed nonce back in the device. Upon successful validation, the device unlocks, at which point you're allowed to rotate keys, transfer sort of back to DOT enabled or with no owner, et cetera. What do we gain from mutable locking, right? So what are the pros? Well, the real pro that you gain with mutable locking over volatile is you've gained this resiliency over power cycle, which is reflected in sort of two, I'll say, sub-bullets, right? The first one is you've eliminated the requirement to stream keys. Your keys are now persistent over power cycle, so you don't have to worry about getting the right key in the right place at the right time because it's going to last over a power cycle. Second, if you think back to the diagram I showed on like the second or third slide that showed Jeff's sort of sliding spectrum of device ownership transfer, we've taken a step to the right? We've now provided additional security assurances to device owners, right? Which is obviously a positive benefit. Now, what about cons? Well, the cons, this is basically the inverse of volatile, right? Because we've now locked the device and it's locked over a power cycle, we now have additional lifecycle complexity. And practically speaking, what that means is that if you want to rotate any keys, you want to decommission the device, you want to scrap the device, you're going to have to unlock the device. And in order to unlock, you have to go through that whole authorized unlock flow that I described before. Now, the third DOT archetype is interesting because I consider it a DOT archetype, but as you can tell, excuse me, really what you're doing is you're turning DOT off, right? And DOT disabled, whenever I think about this DOT archetype, I actually think about, I apologize, I don't remember what the context was, but we had an OCP call earlier this year, and Jeff Anderson from Google made a comment about how we need to be careful that while we're doing our good work at OCP, we aren't building things that are only for power users or can only be used by power users, right? And I think about this often where like not every device owner wants ownership transfer. Not every device owner needs ownership transfer, right? They might just want to, they just want status quo, and this whole conversation isn't very interesting to them. So really, when we look at the pros and cons of DOT disabled, you have to imagine that we're comparing it not to the other DOT archetypes in terms of enabling or allowing DOT with volatile or mutable locking. We're really comparing it to the status quo today, where potentially there are a lot of devices that don't support ownership transfer at all. But what exactly is DOT disabled? So we've skipped over the owner signing key, and all we have is the owner locking key. We store that owner locking key in non-volatile storage, again, so that it's persistent across a device power cycle. We then use the device vendor keys for signature validation during firmware update and secure boot, and we explicitly disallow installation of the owner signing key when the device has the owner locking key installed. So put more bluntly, we've installed the owner locking key, we've locked it such that it only uses device vendor keys, and you're not allowed to install an owner signing key. So you've locked it to continue using device vendor keys. And similar to mutable locking, rotation of the owner locking key or reverting back to the DOT enabled state requires authorization via that same authorized unlock operation that I explained on the prior slide. So pros and cons of DOT disabled, remembering again that we're comparing it not to the other DOT archetypes, but to potentially a world where a device vendor has to make multiple SKUs, where one SKU doesn't support ownership transfer at all, and another one only supports volatile and mutable locking. DOT disabled provides simplicity, right? You can have one device that allows you to turn off ownership transfer. It also allows you to use volatile or mutable locking, right? And it also provides the nice benefit of preventing usage of ownership transfer if a device owner is simply just not interested in using it, right? But they want to make sure that their device can't have ownership yanked out from underneath them. But what's the con? Well, again, if you compare it to a device today, status quo, that shows up, doesn't support ownership transfer, obviously DOT disabled requires action. You ingest the device, you have to install a public key in it. At that point, you've disabled DOT. So a state diagram. I hope that the state diagram helps kind of connect everything, right? So I mentioned earlier on that this architecture kind of leans into attestation, right? So obviously at the beginning, we attest to the state of the device. We ensure that it's not currently owned. We make sure there's no keys in it. We make sure all sort of the various states are as expected for, say, a fresh device, brand new from device vendor. In that state, the device has the device vendor keys in it. The device can boot using the device vendor keys. It allows firmware update using the device vendor keys, but it also allows you to transition to either the volatile state or the DOT disabled state. So we're going to go across the top horizontally through volatile and mutable locking. So as we go into volatile, first we perform the owner signing key installation. That owner signing key is then stored in volatile storage in the device, along with the pre-existing device vendor key, which is ostensibly infuses, something of the sort, right? This is where the edit and no edit piece comes into play, right? So in volatile, if you have an edit device, only the owner signing key will be used for signature validation during boot and update. If you have a no edit device, we would use both the owner signing key as well as the device vendor key, similar to a dual signing scheme. Now, if we transition from volatile to mutable locking, all we're doing is we're installing the owner locking key, at which point we move the owner signing key from volatile storage to non-volatile storage. We put the owner locking key in non-volatile storage. We then apply the same construct I just described for edit and no edit. An edit device would use the owner signing key. No edit would use owner signing key in combination with device vendor. Now that we're in the mutable locking state, you can power cycle the device. All the keys remain. You could ship the device off to somewhere else, boot it up, same thing applies, keys are still there. But how do we return from mutable locking back to volatile? Well, we perform that authorized unlock operation that I described before. You generate something like a unique one-time nonce on the device, countersign it using the private portion of the owner locking key pair. You install it back in the device. Upon successful validation, device unlocks, transitions back to the volatile state. We actually move the owner signing key from non-volatile storage to volatile storage. And at that point, you're in volatile. You could continue operating the device in volatile. You could do what you want. Say you want to go back to default state. All you do is power cycle the device. The owner signing key is lost. We're back to that default starting state where we rely solely on the device vendor keys. Now we'll go down to DOT disabled. We skip over installing the owner signing key. All we do is install the owner locking key. So we have the device vendor key and the owner locking key. With the owner locking key being in non-volatile storage, we disallow installation of the owner signing key. That's obviously my large red X. And in this state, we rely solely on the device vendor key, regardless of the edit and no edit constructs don't really apply anymore, right? Because at this point, you're just installing whatever firmware the device vendor provided. But if you felt so inclined to either rotate the owner locking key or you wanted to return back to the default state, you perform that same authorized unlock operation that I described before, and you return back to the default state. So I hope that the state diagram sort of helps make the flow between DOT states make sense, and sort of how we envisioning being able to transition a device from their default state to the volatile state to mutable locking as needed. I don't think it's expected that in the normal life cycle of a device that a device owner would really flip between states like what I'm describing today. I think that a device owner would choose based on their respective security policy the appropriate device ownership transfer archetype that they would want to use, and they would basically transition directly to that state upon device ingest. So again, my example is somebody who's just really interested in going through the full state diagram. So with all of that said, I'd like to spend a couple minutes talking about how, even though I just spent a bunch of time talking about DOT archetypes, I think that DOT is really only the beginning. And the reason that I say that is because all the supporting pieces that are required for ownership transfer, so the things that sound easy, but they start to add up, right? Like firmware structure. Like firmware structure is not common across all device types. We all know that, right? Where does the signature go? What are you generating the signature over? How do you generate the signature? All of these things are generally unique per device or unique per class of device, right? What about, to my earlier comment around power users, right? Familiarity with general crypt is not as commonplace as we all like to think it is, right? So being able to sort of bootstrap people and understand, okay, these are the keys you need to generate, providing examples, whether it's using OpenSSL or using their existing HSM infrastructure, integrating that into their signing flows, understanding how they would integrate, for example, say a device vendor provides tooling, right? Both binary as well as source to enable a device owner to sign and build, say, edit firmware, right? There's a lot of pieces there that have to integrate with the device owner's existing firmware build, existing signing flows. That's a lot of work, right? What about the actual interfaces for performing device ownership transfer? Do we do this via SPDM? Do we do this via PLDM? There's a lot of uniqueness there. Even the key formats. Do we do raw public keys? Do we do something like PEM? Or even the algorithms, right? We use ECDSA, RSA, when PQC. What does that look like? And my belief is that all of these items, it basically results in more work with more device uniqueness than DOT itself, than all the prior slides I described. And I think that one of the things that we need to work on at OCP, as we bring this work to OCP, is figuring out how far down this path we go. Like how much of this stuff do we specify? How much of it is specified at OCP? How much of it sort of lives elsewhere? To me, that's a very important part of the conversation that I want to spend time on. So the call to action. So I hope that everybody sort of has the takeaway that the future is bright. We have a draft document. It's about a dozen pages long. Now that I have shared all of this publicly, we can share that draft document with everyone, and people can throw rocks at it as they feel so inclined. But the future is complicated, right? It's bright but complicated. So I ask that everybody participates in the Q&A. I think we should have a fair number of minutes to be able to ask some questions. I ask that you join the conversation and help contribute to creating a specification here at OCP. I ask that you holler at me if you have any questions. This is my email, chillier@nvidia.com. I say my email because I know that nobody has seen the draft document yet, so it's easier just to approach me in the meantime before that document is available. And I also ask all device vendors to implement DOT once we have a finalized spec. So I guess with all that said, are there any questions? I expected a lot of yelling. I see David.
I promise not to yell. Any thought to what to do in the case where the device locking key has been installed and the owner has lost or destroyed the private portion, so the authorized unlock mechanism is not going to work?
Yes. So we have a lot of thoughts in that area. Those thoughts are captured in the draft document that I mentioned. Ultimately, I think that from the existing OCP document on this topic, I don't think there's a lot of change from what's in that document, right? Which is you're sort of forced down a path where either the device owner has to make a policy decision of whether they say, no, I will not allow the device vendor to have a key pair that's still installed in the device and allows them to unlock it. But I accept, for example, the RMA cost associated with that or the repair cost associated with that in case of device failure. Or we have to find alternate mechanisms. I think the existing OCP document, I think I actually copied that almost verbatim into the one that we're going to share. Core?
Yeah. In your presentation, you mentioned that you're storing these keys in non-volatile storage. What is that? Is that eFuses or something else?
Yeah, so good question. So existing, I can't talk about the NVIDIA Grace architecture. I can't talk about what we've done on Grace. The existing OCP spec that we've shared does not define the specific types of storage. That's currently an exercise left to the reader. And that's something that I expect we'll have to work at OCP about exactly what that looks like, because obviously the capabilities depend on device type and what they have access to. Paul?
Edit, no edit. So what governs that? Can you change that? Is that something that the device vendor dictates?
Yeah, generally dictated by the device vendor.
Okay. And no plans to offer a way for that to be changed after? So like that'd be a SKU that gets sent out that is going to be locked down one way or the other?
Yeah, I mean, I think you could, I can imagine a world where a device vendor potentially offers a range of devices where, say, I mean, an example could be, I'm thinking BMC is top of mind because of Elaine and Darpana, right? So there's a world where a BMC vendor could offer BMCs where you have one where all you allow is a software stack or firmware stack where you can dual sign it, and another one where you can actually edit full stack like OpenBMC, right? And maybe that's two different device SKUs. I'm not sure.
And I had a thought on David's question. Have you guys, I don't know, in this spec, is there something like a PSID, like with TCG Opal, so if you have physical ownership of the device, you could use that to...
Yeah, not currently in the spec, but it's an open that's identified as an action item.
Awesome. Cool.
Any other questions? I still expected more yelling. Okay. Thank you.